Welcome back. My name is Clayton. This is the bond association enthalpy practice problem quiz, going over the problems. Question 1, all bond dissociation values are positive because an input of energy is required to break bonds. True or false? If an input of energy is required to break bonds, that is a true statement. Input, if we're putting energy into a system, that is a positive change for the system. So maybe we'll just write this out real quick. So if I'm here, say I have an energy level that's here, I put energy into the system, now it's up here. Well, the change from here to here, that is positive. So it better be a positive value. That is a true statement. Question 2, identify each component of the reaction coordinate diagram. Okay, so in this reaction coordinate diagram, letter A, that is this value right here. And that is basically from this point getting up to here. That's what we're measuring here. That is the activation energy, E sub A. That's activation energy in the forward direction. We're moving this way towards our B transition state. Letter C, that is the, let me get a different color maybe. Letter C, that's our reactants. And if we end here, that's our products. That's going to be the overall change in enthalpy of the reaction. Change in enthalpy, change in energy, that is a state function, which means we don't really care about the path all that much. We don't care about the path. What we care about is where did you start and where did you end? Letter D. Okay, so now if I happen to start down here by the products, by F, this much energy is required to get to the transition state. Well, what's the transition state? That is the point where bonds are breaking and forming at the same time. It's the highest point of energy in a reaction. And so to reach that point where bonds are breaking so that they can either continue to form our reactants or go back down here from this direction and form our products again, and energy must be input into the system to reach our transition state. The energy required to reach the transition state, that's what activation energy is. So this would be the activation energy, similar to letter A, but it is in the reverse direction rather than the forward direction. Letter E, that's of course the reactants. Letter F, that is the products. All right. Okay, yeah, I'm just go ahead and read through this. A stronger bond is a more stable bond. If something is more stable, it requires more energy to be put into it to break. So let's just kind of symbolize that here. If I have this as some reaction coordinate, right? We just looked at this. So there's energy here. This is the progression of the reaction here. Here's my reactants. Here's my products. So let's look at the activation energy here. That's the energy required to reach our transition state from the reactant side. And then from here, it's much bigger over here. So if I asked, what does the reactant or the product, does it have more stable bonds? I would say that this side of the reaction has more stable bonds because in order to break them, I have to put into this system a much more substantial amount of energy. Here, these bonds must be weaker because I only have to put in this much to reach that same transition state where the bonds are broken. And then the final option here is shorter, longer, or the same length. A shorter bond is a stronger bond. So that's just another little fun fact there for you. Okay, for number 4, this is using the enthalpy of formation to solve for the change in enthalpy in the reaction. So I know if I have enthalpies of formation, I'm going to have delta H reaction equals the sum of the enthalpies of formation of the products minus the sum of the enthalpy of formation of the reactants. Delta, that symbol right there, is final minus initial. Well, what's our final state? Our final state is the products. Our initial state is the reactant. So that's, again, this is intuitive. It makes sense, right? Now here we're given values for the enthalpies of formation. So I'm just going to, I'll set up my problem, and then I'll plug them in, and we'll solve. So now we have the products minus reactants. So I'm going to say delta H of the reaction equals, we have 6 waters. So I'll say 6 times, this is how I write it out personally, 6 waters plus 6 carbon dioxides minus the quantity of 1 C6H12O6, this is glucose in particular, plus 6O2. All right, so now all we have to do is plug the numbers in from the table that's given, and we're done. Well, I mean, we have to use a calculator. I'm going to make this a little smaller. Okay, so now delta H of the reaction equals 6 times, now H2O, that is negative 241.8, and this is in kilojoules per mole. This 6, that's 6 moles. 6 moles. Plus 6 times CO2, so negative 393.5 kilojoules per mole, minus the quantity of the glucose, that's going to be negative 1273 kilojoules per mole, plus 6 times, well, my table doesn't have a value for the oxygen. Why not? The reason why it doesn't have a value is because as chemistry students, we need to know that the enthalpy of formation of any compound, or not any compound, any element in its natural form, so oxygen as a gas, iron as a solid, iodine as a solid, bromine as a liquid, mercury as a liquid, right? Any element in its natural form has an enthalpy of formation of big old goose egg, 0. So that's going to be 6 times 0 here. All right, so now we just plug this into our calculator. So I'm going to get 6 times negative 241.8 plus 6 times negative 393.5 minus a negative, so that's going to be plus in my calculator, plus 1273 equals, I get negative 2,538.8 kilojoules. That is the change in enthalpy of the reaction, which is why your body uses this particular reaction to create ATP, because look how exothermic it is. This energy that is released allows us to do work on the surroundings. All right, question number 5. We have CH4 plus 2Cl yields CH2Cl2 plus 2HCl. And this time we don't have enthalpies of formation, we have bond dissociation enthalpies. So when we're using bond dissociation enthalpies, we know that it requires energy to break bonds, and it releases energy to form bonds. So our overall equation, delta H reaction, equals bonds broken, I just wrote an X when I meant to write a K, minus bonds formed. because these are going to be positive values, and this negative, turns when we distribute it, turns them all into, the released version of the bond association enthalpy. All right, so now we have to identify the bonds that broke and the bonds that formed. So what I'm going to do, like a nice strategy, sometimes it can be hard to see. So a strategy that I use is sometimes I'll just write out all the Lewis structures, not all the electrons, but the general structures of these compounds. So I can see exactly what broke and exactly what formed. And then we have HCl, HCl. Okay, so now if I look on the reactant side and I compare that to the product side, I lost 2 hydrogens from my methane over here on the left. So bonds broken, if I'm just going to start adding those up, I can say 2 CH bonds were broken. Let's talk about formed. Now, if they're broken, then this carbon has just 2 H's on it, and it somehow got 2 chlorines. Well, obviously 2 CCl bonds formed. Now let's compare some of our other stuff. Here, a ClCl compared against an HCl. And that happened twice, I can see. And so I can say 2 chlorine-chlorine bonds broke and 2 hydrogen-chlorine bonds formed. So if I'm setting this equation up, I can just get these values and total them here. Get these values and total them over here, and add them all together. Well, and do my bonds broken minus bonds formed. So bond association enthalpy for the CH, that is 435 times 2. Chlorines, we have 242, and that's times 2 bonds as well. So whatever that is going to add up down here. And I'm going to subtract whatever this adds up to down here. So the carbon chlorine, that's going to be 351 times 2. And the hydrogen chlorine, that's 431 times 2. So you can use whatever strategy works for you. What I'm doing right now, that works for my brain. So now I'm gonna take care of our bonds broken real quick. So I get 435 times 2 plus 242 times 2. That gives me 1354, and this is all in kilojoules per mole, or kilojoules, that's per bond broken, I guess. No, it is per mole, I'm sorry. And we have 1 mole here, 2 moles here, blah, blah, blah. Anyway, so here I get 1354, and this is going to be kilojoules for our energy. Now we're going to subtract the bonds formed. So let's add the bonds formed together now. So the carbon chlorine, 351 times 2 equals 702 plus 431 times 2 equals 1564. So now I'm going to get 1354 bonds broken minus 1564, the bonds formed, equals 210 kilojoules. There we go. There's our answer.
Hey, so I am editing the video right now, and I just realized the mistake that you probably noticed just now as well. That is not a positive 210, that is a negative 210. So instead of getting my whole camera set up again, I figured I'd just shoot it off my little webcam from my MacBook. So sorry for the crappy quality here, but it is what it is. Sorry about that. Just keep in mind that is a negative 210 kilojoules, not positive. All right, back to the video.
Okay, well, I think that does it for all these quiz questions, some practice problems, think about things maybe a little differently. Once again, my name is Clayton. I am one of the tutors with the Natural Sciences Tutoring Center. Hopefully you found this helpful. And if you ever need any assistance with your class or any of your other science classes, please feel free to come by the tutoring center and we will be happy to help you. All right. Take care. We'll see you.